In this video, I'd like to start talking about how to multiply together two matrices. We'll start with a special case of that, of matrix vector multiplication, of multiplying a matrix together with a vector. Let's start with an example. Here's a matrix, and here's a vector, and let's say we want to multiply together this matrix with this vector. What's the result? Let me just work through this example, and then we will step back and look at just what the steps were. It turns out the result of this multiplication process is going to be itself a vector. And I'm just going to work with this first, so later we'll come back and see just what I did here. To get the first element of this vector, I'm going to take these two numbers and multiply them with the first row of the matrix and add up the corresponding numbers. So I'm going to take 1 multiplied by 1, and take 3 and multiply by 5. And that's what? That's 1 plus 15, so that gives me 16, and that 16 here. Then for the second element, I'm going to take the second row and multiply by the vector. So 4 times 1 plus 0 times 5, which is equal to 4. So 4 there. And finally, for the last one, I have 2, 1 times 1. 2 by 1 plus 1 by 5, which is equal to 7. And so I get a 7 over there. Okay? And it turns out that the result of multiplying that's a 3 by 2 matrix by a 2 by 1 matrix is also just a two-dimensional vector. The result of this is going to be a 3 by 1 matrix. So that's why I get a 3 by 1 matrix. In other words, a 3 by 1 matrix is just a three-dimensional vector. So I realized that I did that pretty quickly, and you're probably not sure if you can repeat this process yourself, but let's look in more detail at what just happened and what this process of multiplying a matrix by a vector looks like. Here are the details of how to multiply a matrix by a vector. Let's say I have a matrix A and want to multiply that by a vector x. The result is going to be some vector y. So the matrix A here is an m by n dimensional matrix, so m rows and n columns, and I'm going to multiply that by an n by 1 matrix, or in other words, by an n dimensional vector. It turns out this n here has to match this n here. In other words, the number of columns in this matrix, so the number of columns, n columns, number of columns here has to match the number of rows here, or has to match the dimension of this vector. And the result of this product is going to be an m dimensional vector y. Okay, so in other words, the number of rows here, m, is going to be equal to the number of rows in this matrix A. So how do you actually compute this vector y? Well, it turns out to compute this vector y, the process is to get yi, multiply a's ith row with the elements of the vector x. So here's what I mean. In order to get the first element of y, that first number, whatever that turns out to be, we're going to take the first row of the matrix A and multiply them one at a time with the elements of this vector x. We'll take this first number multiplied by this first number, then take the second number multiplied by the second number, with this third number, whatever, multiply the third number, and so on until we get to the end. And then we're going to add up the results of these products, and the result of adding that up is going to give us this first element of y. Then when we want to get the second element of y, so this element, the way we do that is we take the second row of A and we repeat the whole thing. So we take the second row of A and multiply elements-wise with the elements of x and add up the results of the products, and that would give me the second element of y, and keep going to get, and then I'm going to take the third row of A, multiply elements-wise with the vector x, sum of the results, and then I get the third element, and so on until I get down to the last row. So, okay? So that's the procedure. Let's do one more example. here's the example. So let's look at the dimensions, right? Here, this is a 3 by 4-dimensional matrix. This is a 4-dimensional vector, or a 4 by 1 matrix. And so the result of this product is going to be a 3-dimensional vector. So we write a vector with room for 3 elements. Let's carry out the products. So for the first element, I'm going to take these 4 numbers and multiply them with the vector x. So I have 1 times 1 plus 2 times 3 plus 1 times 2 plus 5 times 1, which is equal to, that's 1 plus 6 plus 2 plus 6, which gives me 14. And then for the second element, I'm going to take this row now and multiply it with this vector. So I start with 0 times 1 plus 3. Okay, so 0 times 1 plus 3 times 3 plus 0 times 2 plus 4 times 1, which is equal to, let's see, it's 9 plus 4, which is 13. And finally, for the last element, I'm going to take this last row. So I have minus 1 minus 1, minus 2, or this is plus negative 2, I guess, times 3 plus 0 times 2 plus 0 times 1. And so that's going to be minus 1 minus 6, which is negative 7. So that's negative 7. Okay, so my final answer is vector 14. Just to write it out without the colors. 14, 13, negative 7. And as promised, the result here is a 3 by 1 matrix. So that's how you multiply a matrix and a vector. I know that a lot just happened on this slide, so if you're not quite sure where all these numbers went, feel free to pause the video and so take a slow, careful look at this big calculation that you just did and try to make sure that you understand the steps of what just happened to get us these numbers 14, 13, and 7. Finally, let me show you a neat trick. Let's say we have a set of 4 houses, so 4 houses with 4 sizes like these, and let's say I have a hypothesis for predicting what is the price of a house. And let's say I want to compute, h of x for each of my 4 houses here. It turns out there's a neat way of posing this, applying this hypothesis to all of my houses at the same time. It turns out there's a neat way to pose this as a matrix vector multiplication. So here's how I'm going to do it. I'm going to construct a matrix as follows. My matrix is going to be 1, 1, 1, 1 times, and I'm going to write down the sizes of my 4 houses here. And I'm going to construct a vector as well. And my vector is going to be this vector of 2 elements. That's these minus 40 and 0.25. That's these 2 coefficients, theta 0 and theta 1. And what I'm going to do is take this matrix and that vector and multiply them together. Right? That times is this multiplication symbol. So what do I get? Well, this is a 4 by 2 matrix. This is a 2 by 1 matrix. So the outcome is going to be a 4 by 1 vector. So let me, so this is going to be a 4 by 1 matrix is the outcome, or really a 4-dimensional vector. So let me write in one of my 4 elements, we have 4 raw numbers here. Now it turns out the first element of this result, right, the way I'm going to get that is I'm going to take this and multiply it by the vector. And so this is going to be minus 40 times 1 plus 4.25 times 2104. By the way, on the earlier slides, I was writing 1 times minus 40 and 2104 times 0.25. The order doesn't matter. Minus 40 times 1 is the same as 1 times 0.4. And this first element, of course, is h applied to 2104. So it's really the predicted price of my first house. Well, how about the second element? Hope you can see where I'm going. To get the second element, right, I'm going to take this and multiply by my vector, and so that's going to be minus 14 times 1 plus 4.25 times 1.416. And so this is going to be h of 1416. Right. And so on for the third and so on for the third and the fourth elements of this 4x1 vector. And just be clear, right? This thing here that I just drew the green box around, that's a real number, okay? That's a single real number. And this thing here that I drew the magenta box around, the purple magenta color box around, that's a real number, right? And so this thing on the right, this thing on the right overall, this is a 4x1 dimensional matrix, it's a 4-dimensional vector. And the neat thing about this is that when you're actually implementing this in software, so when you have 4 houses and when you want to use your hypothesis to predict the prices, to predict the price Y of all of these 4 houses, what this means is that you can write this in one line of code. When we talk about Octave and programming languages later, you can actually write this in one line of code. You write prediction equals my data matrix times parameters, right? Where data matrix is this thing here, and parameters is this thing here, and this times is a matrix vector multiplication. And if you just do this, then this variable, prediction, sorry about my bad handwriting, but if you just implement this one line of code, assuming you have an appropriate library to do a matrix vector multiplication, if you just do this, then prediction becomes this 4x1 dimensional vector on the right that just gives you all the predicted prices. And the alternative, to doing this as a matrix vector multiplication would be to write something like, for I equals 1 to 4, right? And you have, say, 1,000 houses, it'd be for I equals 1 to 1,000. You have to write a prediction, of I equals, and then do a bunch more work over there. And it turns out that when you have a large number of houses, if you were trying to predict the prices of not just 4, but maybe of 1,000 houses, then it turns out that when you implement this in a computer, implementing it like this, in any of various languages, this is not true only for Octave, but for C++, Java, Python, other languages as well. It turns out that by writing code in this style on the left, it allows you to not only simplify the code, because now you're just writing one line of code rather than a for loop with a bunch of things inside. But for subtle reasons that we'll see later, it turns out to be much more computationally efficient to make predictions on all of the prices of all of your houses, doing it the way on the left than the way on the right, than if you were to write it in for loop. And I'll say more about this later when we talk about vectorization. But so by posing prediction this way, you get not only a simple piece of code, but a more efficient one. So that's it for matrix vector multiplication, and we'll make good use of these sorts of operations as we develop the linear regression and other models further. But in the next video, we're going to take this and generalize this to the case of matrix multiplication.